Our next speaker for the day is Mr. Moinak Shen. He is Director Business Brio, and his topic for the day is Density-Based Clustering, DBSCAN and OPTICS. Moinak Shen heads the analytics practice as Director at Business Brio. He has varied experience both in industry and academia, with companies like Thermax, Infosys, Dhaka Research, US. Moinak is an active practitioner in data science with wide interests in mathematical models and their applications in addressing business-specific problems. He holds a bachelor's degree in engineering from Jadavpur University, Kolkata, and a full-time MBA from Michigan State University, with dual majors in marketing and supply chain management, and was also a graduate scholar at Purdue University, USA. Mr. Moinak Shen, please.
Good afternoon, everybody. I'm going to talk about a particular family of clustering algorithms. It's a little bit of a technical talk, maybe compared to some of the others. I hope you don't find it too boring. And it's a little longish. Am I audible? I still need this? Okay, so this is what we are going to do. I'm going to have a brief introduction, some examples, key ideas, and then a main algorithm called Dbscan, and I'll take a few questions at the end if time permits. So as many of you probably know that clustering is one of the main areas of application in data science, and so it's basically given a set of data points, how to partition it so that the most similar points land up in the same clusters. Many business applications of clustering, starting from customer segmentation. Probably the most classical application is in marketing, customer segmentation. And then collaborative filtering, recommender systems. I believe Nirupam was talking about recommender systems earlier today. So clustering is actively used in some of the recommender systems. And of course, numerous technology applications, multimedia data analysis, including text, how to cluster them, dynamic trend detection, sort of also related to anomaly detection, and then trajectory analysis. I have an example later on. So if you think about clustering, classically there used to be two approaches. One was the model-based approach, like mixture models. And then there was the distance-based approaches, which again had the flat models, which are like the classical K-means kind of clustering, and then hierarchical ones. What I'm going to focus on today is something called density-based clusters, which we'll see. And then there are other kind of clustering algorithms like NMF and spectral clustering. NMF is non-negative matrix factorization. So why do we have this density-based methods? The main reason is that the classical methods have serious drawbacks. Number one, they require domain knowledge a priori. So for example, if you are doing K-means clustering, you need to know the number of clusters in advance. So it's ill-suited for convex clusters. Ill-suited for non-convex clusters. Efficiency issues. So if you have really big data and huge data sets, they don't scale. And the last point, no ways of handling outliers, noise, or anomalies. And we'll see an example. So this arises from the fact that if you are doing a K-means kind of cluster, each and every point must be assigned to a cluster. So there is no concept of an anomaly or a outlier or a noise. So I'll begin with few synthetic examples. So here are three data sets, and if you think about them, if you run classical clustering algorithms like, say for example, K-means on this, you will probably not get good results. So if you do K-means here, for example, the first data set here, you see 4 clusters, right? The problem here is that the central cluster is disproportionately large compared to the other 3. So if you do K-means with K equal to 4, it will give you 4 clusters, but the clusters will be wrong. Similarly, the other one there, the problem there is that the clusters are non-convex. And again, there are 4 clusters there, but if you do K-means with 4, you will get 4 clusters, but again they will probably be wrong. And finally, if you look at this bottom one, 4 clusters there also, but you see the isolated points, those are the outliers or noise, and classical clustering would give you this. Whereas, if you use density based methods, you get the right clustering. And this is kind of, as I said, this is a synthetic example, but I am just trying to make a point. Now coming to some real examples, where is it applied? So for example, this one, this is a crime data. You have crime data on a city and you want to identify crime hotspots. So the left hand panel, that one is the output from a K-means kind of a cluster. And you see it has identified zones and the red dots are the centroids. Whereas if you run a density based DBSCAN, you get the right hand panel, where you actually have the pockets identified. I'm sorry, the colors are a little fuzzy, but I hope you can make out the difference. So it's giving entire parts of the city. The K-means it's giving entire parts of the city as hotspots, but the DBSCAN is much more specific. Here is another example. This is forest data from California. It's an open source database, and this again the coloring is probably not proper, but you can make out the different zones, and these zones are mostly non-convex kind of grouping, and this is only possible with DBSCAN kind of density based methods. This is a satellite image of Mumbai, and so it was, this picture was fed into the input as an input to the clustering algorithm, and that's what you get in the output. So pretty accurate. So it has got the clusters pretty correctly. A different example from medicine. So this is skin lesions from a dermoscopy examination for different kinds of skin lesions. And you see the blue border. The blue border is what the machine has identified through DBSCAN, and the red ones are what the expert or the dermatologist has identified. So you see pretty amazingly good match. The final example is what I was talking about. This is very new. I think it's just this came out only this year, I believe. So this is what is called trajectory analysis. So thanks to modern day GPS enabled cell phones, you can roam around with your GPS on, and it can identify where exactly you are spending your time when you are shopping versus when you are in the office, when you are at home. And so this is actually taking real-time data of your coordinates and trying to cluster your locations. So I'll just quickly go through the key ideas. So the key ideas are that the key idea is a neighborhood. So you have to define a neighborhood around a point. And then there is the concept of a density of a neighborhood. I'll just skip the math and just illustrate it through a picture. So you see this ball here, and it's a ball of a certain radius, and you define that radius a priori, and that within that radius how many points lie. That is basically the density of that neighborhood. So the green circle is your neighborhood, and how many points are there within that circle is your density of that neighborhood. So if you shrink the ball, then obviously your density also goes down. Now the next idea is there are different kinds of points. So you have points which are directly reachable from points which are called core points, and then you have points which are density reachable. And again, these are just terms I will illustrate, and then there are density connected points. So for example, the green circle there, you see this blue dot in the middle of that green circle. So if that is your central point, all these three red points are directly reachable from that green point. But whereas if you look at the red point here, this point here, that is not directly reachable, but you can hop to that point from a point which is directly reachable. So that is called a density reachable point. So that's just how it is defined. So this is density reachable. And then there are the concept of the core points and border points. So basically there are, I will just go through these slides. So there are three kinds of points, core points, border points, and outliers, as I said, noise. So if you look into this diagram, the red points are all core points because you can jump from one to the other directly. The yellow points are the border points, and that blue point there is the outlier because you cannot jump to that point from any of these points. So this is a technical definition of two conditions of clusters. So you have a maximality condition that any 2 points which are density reachable are part of the cluster, and if a point is density reachable from any other point, then it is part of the cluster also. So coming to DBSCAN, this is a pretty old algorithm, but it's being increasingly used nowadays. It's about 20 years old. And the algorithm goes like this, that you pick an unassigned point at random and compute its neighborhood. If it's a core point, then start your cluster from there, else you make it as an outlier. In step 2, you try to expand your cluster, and you expand it by adding all the points, either all the points which are either directly reachable from the points or which are density reachable from the core. So if an outlier has been added, change its label to a border point and repeat the steps 1 and 2 till all the points are labeled. So it's just a simple iterative step, and you go through this loop. That is pretty much it. So if you have any questions, I'll take a couple. Yes.
When you are using that DBSCAN algorithm, unlike Kmean or Kmedian, it will not be the elliptical shape.
No, it will not. That is one of the main things I mentioned, that it K-means is restricted to convex sets. So it has to be convex. I mean, whatever you get out of K-means will always be a convex set. But and that is why it cannot identify shapes like this. That is why it cannot identify shapes like this ones.
Which is an advantage of DBSCAN.
Correct.
Now, when those maximality and connectivity, are these the two main criteria by which it completely identifies the cluster in DBSCAN? Or, I mean to say, when you, the condition, two conditions what you have said, maximality and connectivity, is that,
Yes.
does that sufficiently defined.
Those are the properties of the points which define a cluster if you have applied the DBSCAN algorithm. So if you have applied the DBSCAN algorithm and it comes up with the clusters, then these two conditions will automatically be satisfied. These are the properties of the DBSCAN clusters. Yes, yes.
So suppose in a real world data set, there is a number of attributes or features which are continuous and some of them are discrete. So is it applicable to this kind of a data set?
That's a very good question. Typically, DBSCAN will not perform optimally if you have non-continuous data.
Okay.
So see whenever you are talking about a neighborhood of a point, implicit in that definition is a definition of a distance. So you have to define a distance metric, right? So if you have a continuous data, you can define something like an Euclidean metric or a Manhattan metric to define the distance. But if you have discontinuous data, I mean discrete data, then you have to come up with an appropriate definition of an underlying metric, of a distance metric. And the performance of this algorithm will critically depend on how you define that distance metric.
Thanks a lot.
Okay, thank you.
Thank you, Mr. Sen. I'd request you to be around because we'll call you for your felicitation, but there are a couple of announcements before that. I'll go over with the happy announcement first. While Mr. Sen was speaking, I just got informed that Business Brio has been selected as a finalist for the Red Herring Asia 100 Companies. Let us take the opportunity to congratulate Business Brio on this wonderful achievement. A generous round of applause, please. I request the President of Data Science Foundation to come up here and acknowledge your applause, please, on this behalf. I'd like to call on Mr. Moinakshen once more to come to the dais for your felicitation. And to do the honors, I'd request Mr. Anindo Chatterjee, Executive Director, Finance, Webel. Sir, please come here if you are. Okay. So can I request Mr. Nirupam Chaudhary to do the honors, please? Please. Big round of applause for him, please.